We'll start in just a minute. Okay. So let's begin. So we'll talk a little bit more about how to parameterize curves and really kind of vary wildly. But for line segments, there's usually a pretty straightforward process. It is often the case that we're going to, if we're starting at the point like this and ending the point here, we're going to think about this being our starting point when time equals 0, and this being when time equals 1. So then if I want to find my parameterization for x, it's going to be my starting point plus the difference between my end and my start times t. So in this case, -6 minus 2 times t, which we could simplify, and we will in a second. Similarly for y, the starting point or value is 5, and the difference is 12 minus 5 times t. So we could write this more succinctly as x equals 2 minus 8t, and y equals 5 plus 7t. And that would be one way of parameterizing this line segment that begins at the point 2, 5 and ends at the point -6, 12. And you can check for yourself, right? If you plug in t equals 0, you get the point 2, 5. Plug in t equal to 1, you get 2 minus 8, which is -6, 5 plus 7, which is positive 12. But they can be more difficult. For example, we could look at something like parameterizing the, I don't want to write the word parameterize again, parameterize, not parameterize. The part of the parabola y equal to x squared minus 2x minus 8 below the x-axis. So it's usually pretty easy to parameterize something if they've already given you y as a function of x or x as a function of y. we can make the very, very easy choice to just say, well, let x equal t and y equal t squared minus 2t plus, or sorry, minus 8. The only thing here is that that's going to give us the entire parabola. We only wanted the part below the x-axis. If we draw this, just kind of have an idea of how it looks, you might factor that and see that it's going to equal x minus 4 times x plus 2. So the x-intercepts would be positive 4 and negative 2. And it would look something like this. Something like this. But I just want this part here. So all I have to do is say, well, if I want just that part there, x should be between negative 2 and positive 4. And since x is equal to t, I can simply say, well, t has to be between negative 2 and positive 4. And sometimes it's really just that easy. Sometimes, again, I know I keep saying this, sometimes it's not. Let's look at an example that's maybe a little bit harder. Let's parameterize the, which side do I want here? That'll be interesting. Let's do the left half of the parabola. Y equal to x squared plus 6x. Yeah, I mean, again, I think this isn't going to be that bad, except for identifying where the left half starts and end, or the cutoff point for the left half. So parabolas, left and right half, distinguished by where the vertex is. If we were going to draw this, I would probably try drawing it just by identifying, again, the x-intercepts. So if we factor that, that's equal to x times x plus 6. It looks like the x-intercepts are at 0 and negative 6. It's certainly an upward opening parabola, so it's going to look something like this. And it looks like the vertex is going to be at an x value of negative 3. Because it's always the vertex, if there are x-intercepts, the vertex is always exactly in the middle of the two x-intercepts. Or you could use the usual way of finding the vertex, which is minus b over 2a. But that seemed less interesting. I don't really care about the y-coordinate, but if you plugged in negative 3 for x, you get 9 minus 18, which is negative 9. So one way of doing this would be to say, well, I'm going to, again, let x equal t, which feels kind of boring. Y equal to t squared plus 6t. And then say that t has to be, well, if I want the left side, I want t to be, or x to be, same thing in this case, less than or equal to negative 3. Which, kind of weird. I was honestly imagining doing it a very different way, but that totally works. Yeah, that totally works. And I guess I should say, when you're trying to parameterize something, it's usually in your best interest to try to find the path of least resistance, to do it the easiest way possible, even though there might be a slicker way that might be more complicated. So a couple more examples before I move on to doing some calculus with parametric equations. Yeah. So why don't we do, sorry, let me get it here real quick. Let's do that and that. So let's do the following. Let's say I want to number things here. I want to parameterize the ellipse given by the equation x squared over 4 plus y squared over 9 equal to 1, which is a pretty standard way of writing the equation of ellipse. Usually x squared over some square number plus y squared over some square number equal to 1. Alternatively, someone might write this as multiplying everything by 36, 9x squared plus 4y squared equal to 36. But that's less good for us. To me, this always feels a little bit complicated to figure out how to parameterize. I will point out, if we graph this, the major axis is along the y-axis, and we have intercepts. When x is 0, y is going to be +3 or -3. When y is 0, x is going to be +2 or -2. So our ellipse looks vaguely like this. And I should have specified, I suppose, a direction as well. Apologize. Parameterize the ellipse given by this equation in the counterclockwise direction. So here's how I would generally think about this. Ellipses are essentially circles. They're not exactly the same, but they're very close to being the same. And we'll come back to this in a second, but I'll point out that if you wanted to parameterize a circle, x squared plus y squared equal to 1, we generally do this by letting x equal cosine of t, or whatever parameter you like to choose, because we use theta instead, and y equal to sine of t. We're literally just kind of going back to the unit circle and saying that, oh yeah, if you're on the unit circle and your angle is t, the point that's on the unit circle is quite literally cosine of t comma sine of t. And you definitely have the equation cosine squared plus sine squared equal to 1, which is exactly what you get if you sub in cosine and sine for x and y respectively. And this definitely does give it to us counterclockwise, because if you start at t equals 0, you're starting right here. And then as you increase t, as you increase the angle, you go around counterclockwise. So how do we do this? Well, here's how we do it. You're trying to make this same sort of equation come up. So I would really, in fact, sorry, let me back up 1 second. If I sub in x equal cosine and y equal to sine, I'm really getting something like cosine squared t plus sine squared t equal to 1, which is true. So that's what I'm thinking about when I'm trying to parameterize this. I would really like to have cosine squared t plus sine squared t equal to 1. So to make that happen, what I need is x squared over 4 to equal cosine squared of t, which means I need x squared to equal 4 cosine squared, or x to equal 2 times cosine of t. In a similar way, I need y squared over 9 to equal sine squared of t. So I need y to equal 3 sine of t. And this will give us the parameterization of this ellipse. And actually, let's plug in a few points just to make sure it works. So if we plug in time equal to 0, well, cosine of 0 is 1, 2 times 1 is 2, and sine of 0 is 0, so 3 times 0 is 0. So x is 2 and y is 0, so we start right there. And if we plug in, say, time equal to pi over 2, well, cosine of pi over 2 is 0, sine of pi over 2 is 1, and 3 times 1 is 3, so we end up exactly at the point 0, 3. So it totally looks like we're going in that direction. You could plug in a less nice angle, like you could plug in something like pi over 6 if you really wanted to and get some point in between. But this really is working for us. So if you ever have to parameterize an ellipse, keep in mind that you're trying to essentially make this nice trig identity cosine squared plus sine squared equal to 1 show up. And that's what we're doing with this. That's probably enough parameterizing, at least before we get to the calculus part. So let's look at a new thing, something that's a little less easy to draw. So here's some calculus. when we say calculus and parameterized curves, what we really mean is like derivatives, antiderivatives, second derivatives, stuff like that. So that's what we are referring to when we say calculus with parameterized curves. So let's look at this example. So we're going to consider a curve defined parametrically by x equal to t squared, y equal to t cubed minus 3t, where t is any real number. T is between negative infinity and infinity. It's not, I mean, you could solve for t here, but it doesn't really make it easier to graph it. So just as a point, note that if we solve for t, if we get the square root of x equal to t, well, technically, it's really plus or minus the square root of x because t can be positive or negative, as we just noted over here. And if you try plugging that in over here, you would get y equal to plus or minus root x cubed minus 3 times plus or minus root x, which, again, I don't really know what that looks like. If you break it up into two pieces, you either have y equal to x to the 3 halves minus 3x to the 1 half, or the other piece is y equal to negative x to the 3 halves plus 3x to the 1 half. Sure, that's nice, I guess, but again, I don't really have any idea of how that looks. It's not a graph that's typical to us. So instead, if I have something that's not very usual, I'm just going to start plotting points. So let's plot some points. We'll pick some convenient t values like t equal to -2, -1, 0, 1, and 2. And then we'll find the corresponding x and y values. So the x values are easy. X is just t squared. That's going to be 4, 1, 0, 1, 4. The y values we have to do a little bit more thinking for. Y is going to be t cubed minus 3t. So here we're going to get -8 plus 6, which is -2. And then 1 minus 3, which is still -1, apologies. -1 plus 3, which is +2. 0 minus 0, which is 0. 1 minus 3, which is -2. And 8 minus 6, which is +2. So we're going to plot those points just to get a basic idea of how this thing works. And it is kind of nice to plot them in order so you can kind of see the direction of travel. So when time equals -2, I'm going to have an x value of 4 and a y value of -2. So I'm down here. And then later on, when time is -1, I'm going to have an x value of 1 and a y value of +2. So from time equals -2 to time equals 1, I traveled from there to there. And then the next point is going to be 0, 0. So I'm traveling there to there and then there to there. And then the next one's going to be 1, -2. So down to here. And I should label these things. That'd be a smart idea. Grab a pen here. So here's time equals -2, time equals -1, time equals 0, time equals 1, and finally the last one we are plotting, time equal to 2. Question? Yeah. Like up here, kind of to show how terrible it is actually, but really because so if time is plus or minus root x, here is where I'm saying t is positive, where t is positive root x. And over here is where time is negative, where t is negative root x. So I was just showing that. So like really what's happening here is where time is positive, you'd have kind of this part of it here. And when time is negative, it'd be this part of it here, which we're about to graph also a little bit in just a second here. So let me, yeah, you're welcome. Just check one more thing here. Yeah, that's terrible. Okay. This graph is always super funky looking. Okay. I wish the numbers were nice looking. So here's kind of what this looks like. Oh, I'm making stupid mistakes. Yeah. Not stupid mistakes, just forgetting how things work. So here's kind of what this graph looks like. And I'll point out, I made a tiny error here. This arrow here should not be there, because the arrows we draw when we're drawing parametric curves should always be in the direction of time increasing. So that arrow is a mistake. Really, I should draw my arrows this. Time is increasing in that direction. So our arrow should go that way. Like that. And so you can see here, when time is positive, we're getting this portion of the parametric curve. So I guess that's what y equal to x to the 3/2 minus 3x to the 1/2 would look like. You know what we should do? We should pull it up on Desmos, because I think that would look neat. Or at least helpful. I bet Desmos does parametric curve. Oh, I wonder. Now I'm curious. We might find out here. So let's just take a look, because it's always good to learn new things. Let's graph y equal to, so we have x to the 3/2 minus 3x to the 1/2. Yeah, I think that looks pretty good, right? And then the other half of it, which I'm just going to do by doing the same thing and putting a minus sign in front of all of it. Cool. Oh, it's kind of great, I think. I'm curious. I don't know how, I don't know. I don't know if Desmos says parametric curves nice. So let's try it. So let's try letting x equal t squared and y equaling t cubed minus 3t. I'm not confident here. No, but it doesn't look good. I bet if you picked a different letter, it might work. Like if you pick something like something other than a normal variable, like you picked, I don't know, b. Yeah, let's try that. I didn't pick b, I picked t. Sorry, I keep blowing it here. Usually, interesting. Usually they give you an option to like pick a slider. There we go. No, I actually want to delete the b there. Yeah. And then let's try this. It might work. We'll see. I know it's not going to work. Oh well, such is life. Anyway, we still see what it looks like. Kind of great. There's probably a way to do parametric curves on Desmos if you explore it a little bit, and I will explore that later on and see if I can figure it out, because it's probably worthwhile to us. But that's what our thing looks like. So now we want to answer some questions like, what are the x-intercepts? Okay, well, the general idea of finding things is usually still the same as before. We just have to do a little more work. So normally you find the x-intercepts by setting y equal to 0, right? Y equal to 0? Yeah, y equal to 0. So we're going to set y equal to 0. So we're setting really t cubed minus 3t equal to 0. So we're going to end up getting t times t squared minus 3 equal to 0. So either we're going to get t equal to 0, which means x would be 0, because we know that when t is 0, x is 0. Or we're going to get t squared equal to 3, which would result in t equal to plus or minus root 3. But x is equal to t squared. So if t is equal to plus or minus root 3, then x is going to equal plus or minus root 3 squared, which is just going to be 3. So our x-intercept is, well, x-intercepts, I should say, are either x equal to 0 or x equal to positive 3, which certainly graphically seem to make sense. I was having trouble graphing it because I was accidentally thinking that the x-intercept was the square root of 3. I was like, oh, that's not going to look right. And then I remembered, oh, actually be root, actually 3, because x is equal to t squared. So make sure when if you're finding intercepts, you have to find the right t value and then plug it into what x equals to find the right x. Second. Oh, I'm sorry. Someone asked a question and I Totally missed it. Why do I never see the chat here? Good. Well, thank you for asking and answering the question. Good job, folks on chat. And again, apologies. If you see me ignoring your question and you really would like it answered, you are welcome to unmute yourself and say words. And sorry I missed it. I will try to pay better attention to the chat. So the next question is, and this is where we're going to have to introduce something new. Where do we have a horizontal tangent line? So where are the horizontal tangent lines? And I guess this should be more specific. When I say where, I mean at what XY coordinate? Because you might sometimes be asked for what value of t. Usually you're asking like where on the curve do you have that? So how do you find horizontal tangent lines in general? Or what do we know is true when you have a horizontal tangent line? Well, the derivative should be equal to 0. So to find a horizontal tangent, we set the derivative dy dx equal to 0 and solve. There's a problem. We don't know what dy dx is. We know what y and x both are as functions of time. So here's how this works. And it's a little bit, it's actually, the actual calculation is really easy, but the concept is a little bit funky. So let's take a quick aside here. I don't want to think about this. Sure. So what we're really going to do is we're going to imagine that y is some function of x and x is some function of t. So that when we find the derivative of y, we're really finding, sorry, I will admit this kind of throws me off sometimes. Apologies, let me rewrite this here because I'm actually going to start by finding dy dt. So I'm going to say the derivative of y with respect to t. Well, I'm going to use the chain rule. I'm going to say it's the derivative with respect to t of y of x of t. You probably don't need to write this down, although you're certainly always welcome to. So then we're going to use the chain rule. We're going to say, well, that's the derivative of the outer thing, y prime of x of t, multiplied by the derivative of the inner thing, which is x prime of t. But now I'm going to change up my notation to make it look like I want it to look. So on the left-hand side, we're just going to call this, not actually that differently, dy dt. On the right-hand side, y prime of x of t is really just y, it's still y prime of x, right? You're taking the derivative at x. So we really have here dy dx, and x prime of t is the derivative of x with respect to t. So that's really dx dt. So we end up getting, if I want to solve for dy dx, because that's what I'm actually trying to deal with here, is setting dy dx equal to 0. I'm going to divide both sides by dx dt. So we're going to get the dy dx, the derivative of y with respect to x, is kind of conveniently dy dt, the derivative of y with respect to time, divided by dx dt. And although it's not really true, it certainly looks like you could just cancel the dt's and have this dy dx equal to dy dx. Again, not a really true thing, but it looks nice and it makes us think, oh yeah, it's not hard to remember this equation. Dy dt over dx dt is just equal to dy dx. So if we want to find dy dx, we're going to find dy dt and dx dt. So here's what we've got. Oh, can't move these papers. So as a reminder, we have that y was equal to, what was y equal to? As a reminder to myself, y was equal to t cubed minus 3t, and x was equal to t squared. Be careful here. It is really easy to get the order wrong for some reason, because we're always writing x first, but we're putting dy dt on top. So make sure that when you find dy dx, you're putting the y thing on top and the x thing on the bottom. I just say this because I've made this mistake many times in my life. So try not to make the mistakes I've made. Learn from my mistakes. So dy dx is going to equal dy dt divided by dx dt, which is equal to derivative of the top of y is going to be 3t squared minus 3. The derivative of x is going to be 2t. And so if we're trying to find where this is equal to 0, we're just going to set the top equal to 0. And if we solve that, we're getting t squared equal to 1. So t is equal to plus or minus 1. Now we're not quite done because we said we wanted to find the xy coordinate. So if we plug 1 back into the x and the y, if t equals 1, we get the xy coordinate. X is 1, y is going to be 1 minus 3, which is negative 2. And similarly, if t equals negative 1, our xy coordinate is going to be negative 1, positive 2. Which if you look back at the original graph, doesn't seem super surprising. If you look at the graph over here for a second, oh yeah, at the point where time equals 1, or time equals negative 1, it looks like we probably do have a horizontal tangent line. So that seems relatively reasonable. Questions about that so far? So as a reminder, the takeaway from this section, although what we've said is important, but the real kind of takeaway is that dy dx is equal to dy dt divided by dx dt. What if we asked, where does this curve have a vertical tangent line? Okay, horizontal tangent line means that the slope is 0. Vertical tangent line means that the slope is, your line's vertical, what kind of slope do we have? So slope is rise over run. You have no run, you have an infinite rise. Your slope is undefined. So vertical lines have an undefined slope. So we're saying we need to find where dy dx, which is still equal to 3t squared minus 3 over 2t, is undefined. Or in other words, where we're dividing by 0. So set the denominator equal to 0 and solve for t, which is going to be t equal to 0, which is the point x comma y equal to 0. Sorry, x comma y equal to 0, 0. And again, this seems to correspond to what our graph looked like. Look at our graph again. You can see, yeah, it looks like at the origin over here, the tangent line is probably a vertical tangent line, specifically the y-axis. And these are two questions that are probably pretty typical to ask. Like when we were dealing with questions like this, people do ask, where do you have a horizontal tangent line? Where do you have a vertical tangent line? Oh yeah, and then we should do the following as well. What about concavity? I know it's been a while since we talked about concavity. So if a function is specifically concave up, so D. Was I lettering things null before? I'm like just throwing in a random letter. No, let's not throw in a random letter. Sorry about that. There's like all these letters on my notes. The next point here. Where is it concave up and concave down? So reminder, a function is concave up when its second derivative is positive. So we're looking for d squared y dx squared to be positive. And similarly, concave down when its second derivative is negative. So the second derivative is not quite maybe as lovely as you would hope. Here's what I mean. So we have so far that dy dx is equal to dy dt divided by dx dt. And when I first learned this, I really thought it was going to be, well, if dy dx is just the derivative over the derivative, then the second derivative is just going to be the second derivative over the second derivative, and it's not. So let's actually find it. So let me think about this for a second. Sorry, this part was always challenging for me. All right, that's fine. So here's the idea. Before, sorry, I don't like it. Sorry, this always, sorry, sometimes things throw me off, and this is always one of those things like I really have to think about, like, how is this working again? Yeah, this works the way it does. Okay, yeah, that makes sense. Right, okay, so here's what we had before. The derivative with respect to x of y was equal to dy dt for dx dt. And it's important to remember here that y is a function of x. So we're going to do the same sort of thing, but now with y prime. So now we can say that the derivative with respect to x of y prime, well, we can still say the same sort of thing. It's going to be dy prime dt divided by dx dt. I'm not going to lie, that feels a little hand-wavy. Let's go back. Let's go back to what we did before. So I feel like I owe you a better explanation. So, yeah. Yeah. Question, yeah. Sure. That's fair. So when we write it this way, what we're really writing, so when we write d squared y dx squared, we're really saying the derivative with respect to x of the derivative of y with respect to x. You could even really write it as d dx of d dx of y. So the d dx says take the derivative of, and the y is what you're taking the derivative of. So do it once, do it twice. And the reason we write it this way is because you're not squaring the y, you're squaring the operator, essentially. So really, you could write this more annoyingly as d dx squared applied to y. But this is kind of the standard way of writing it, where it's d squared y over dx squared. So yeah, I guess we'll do it that way. Sorry, I'm just, oh, I see. Sure. Sorry, my brain just thinks of it backwards from the way I've written it here. So that's fine. Alternatively, we can think of dy dx still some function of x. So we can write this as like y prime of x. And then x is still a function of t. So if I want to take the derivative with respect to t of my y prime, that's the problem though, I see. Sorry, I've just gotten, I really like thought myself into the wrong headspace here. I'm like, is this gonna work? No, that's not gonna work. Interesting. Can't think of it that way. Apologies. Yeah. Okay. So here's what we do instead. Sorry. Sometimes you have to think of it a different way. So here's the other way we can do it. So what we're going to do is we're going to say, well, dy dx is a function of x. And we're going to, oh, sorry. No, I keep wanting to say that. It's a function of t. And it is, right? If you think about what we did before, we certainly had dy dx in terms of t. From before, our previous example, our dy dx was actually equal to 3t squared minus 3 divided by 2t. So not just making things up, dy dx actually a function of t. And then t, we can think of as a function of x. And I'm gonna write this again because it looks a little bit messy. But I'm writing the same thing, so you don't have to like start over. Sorry, I just don't like how messy that looks. So dy, oh, there's new message. Sorry, I see there's the chat. Yeah. Okay. Yes. Yeah, same thing as y double prime. Sorry, there are questions about the notation. So d squared y dx squared is y double prime. But the reason we're writing it in this other notation is because we want to be specific about what we're differentiating with respect to. You write y double prime, it's not always clear that you're differentiating with respect to x versus t. So especially in this context with parametric equations, it's usually a better idea to write it with the Leibniz notation as opposed to the prime notation or the Newtonian notation. So again, I'll remind you, we have dy dx is a function of t, and t can be thought of as a function of x. And then from last time we had dy dx equal to 3t squared minus 3 over 2t. So literally a function of t. And t is a function of x, right? You can think of, we had x equal to t squared, so you certainly could solve for t as a function of x. Okay, so now here's what we're going to do. We're going to take the derivative of this. We're going to say, well, the derivative with respect to x of dy dx is going to equal the derivative with respect to t of dy dx times dt dx. Yeah, that feels right. Sorry, I feel like I'm not helping. But to be honest, I feel like I'm making this more confusing, to be really honest, because I feel like I'm confusing myself. So I need to back up. Why is this so challenging for me to think of for a second here? That's right. Yeah, yeah. I'm sorry. I'm referring to old notes of mine, and I feel like I've lost my way here. So let's go back. And I have to apologize because I feel like I've said let's go back more than a few times here. So I am sorry. So here's what I want you. Here's what I'll leave you with, because not leave you with, we're not ending class right now. So I think what I was saying before is probably the easier way to think of it. So what we have is, we had before, the derivative of y was equal to dy dt over dx dt. And this worked because we thought of y is a function of x, and x is a function of t. Now we're going to do the same thing. We're going to say, well, now y prime, which is dy dx, is a function of x, and x is still a function of t. So we're basically taking the y here and replacing it with y prime. So, okay, well, the derivative with respect to x of y prime is the derivative of y prime with respect to t over dx dt. And then we can say, well, the derivative with respect to x of dy dx yeah. Right. That's okay. That's where I'm getting lost in. Thank you. Okay. I figured it out. Sorry. I mean, I'm glad I figured it out, but sorry it took me so long. So we've got the derivative with respect to x of dy dx equal to the derivative with respect to t of dy dx. That's where things are a little bit screwy. I was forgetting about that. And then on the bottom, you still have dx dt. So what we have here is your d squared y dx squared, your second derivative, is equal to the derivative with respect to t of the dy dx you found before as a function of t divided by dx dt again. So kind of weird, right? There's no better way to write this. You can't, I mean, I guess, okay, it's not a better way to write it, but a way you could write it that didn't involve any dy dx's is you could write this as d dt of dy dt over dx dt. That doesn't seem better to write, but that's what we have there, right? Because that's what that's equal to. Dy dx is equal to dy dt over dx dt, all over dx dt. So, yeah, a little bit challenging, clearly, for me here. We get things back in order here. All right, so now we can get back to answering the question of where do we have concave up and concave down. So we're actually going to find the second derivative, which gets a little bit messy. Now, really, no matter how simple your first derivative is, your second derivative is always going to be kind of terrible usually. So our dy dx was equal to 3t squared minus 3 over 2t. And I would rather not use the quotient rule if I can help it. So I'm going to, because I'm going to have to take the derivative of this. So let's write this as 3t squared over 2t minus 3 over 2t, which we could simplify as 3 halves t minus 3 halves t to the negative 1. That's going to make it a little bit easier to find the derivative of that for the top part here. So now finding d squared y dx squared, it's going to be the derivative with respect to t of this 3 halves t minus 3 halves t to the negative first over dx dt, which is still 2t. It's kind of funny that the bottom part doesn't really change, but we're just going to have another 2t down there. So there's your dx dt. There's your dy dx. So now we differentiate. We get 3 halves plus 3 halves t to the negative 2, right, just using the power rule, divided by 2. Sorry, not 2, 2t. And then we can make this even simpler by, can we make this simpler? Sure. We can make this simpler by factoring out of 3 halves and saying we have 3/4 really, because 3 halves over 2. Then you have a 1 plus t to the negative second over t. Or probably easier, a 3/4 times 1 plus 1 over t squared plus, yeah, over t. Okay, so concave up versus concave down. So when is this positive, when is this negative? Well, the only time this can change signs is if it's either equal to 0 or undefined. This is never equal to 0 because the numerator is 1 plus 1 over t squared, which is always non-negative. So the only time this is undefined is when t is equal to 0. So if we look at our number line here, when t is greater than 0, the whole thing's positive. So my second derivative, d squared y dx squared, is positive when t is greater than 0. And if t is negative, well, the numerator is still positive, but the denominator is now negative. So when t is negative, the whole thing is negative. So that means my function is concave down when t is negative and concave up when t is positive. Let's go back and look at the picture. So look back at our graph, which I refer back to. Actually, So looking back at our picture for a second. If we look here. So here's where t is positive. Oh yeah, look, it's totally concave up when t is positive. And here's where t is negative. Oh yeah, definitely concave down when t is negative. So certainly the concavity agrees with what our graph is showing us. It just took us a little bit to get there. Okay, that was more painful than it should have been. Sorry about that. Let's continue on. So let's try and keep these notes somewhat in order here. Maybe, maybe not. One second, I'm trying to not get too. Yeah. Let me just double check the chat here. So you guys, so yes, yes, yes. Yeah. Cool. Yeah, you're not the only one asking about my d squared y dx squared notation, but there were people in the chat were also asking that. Let's do another example where we have to do this kind of thing. Trying to keep it. So let's look at this next parametric equation. Let's say we have x equal to t to the fourth plus 1, y equal to t cubed plus t. And we're going to start off by finding the equation of the tangent line at t equal to -1. So finding the equation of a tangent line isn't different than it was before. We still need to find a point and a slope. So once we have our point, which we'll say is going to be x comma y, and our slope, which we'll call m, then our equation is just going to be y, I should call this x1, y1. Y minus y1 equal to m times x minus x1. So our job, just like our job is every time when you're trying to find the equation of a tangent line, is to find the point, find the slope, and then write the equation of the line. So let's start off by finding the slope. So dy dx, just like we just saw, is going to equal dy dt divided by dx dt. Now be careful here. It'd be really easy for me to write the wrong thing. Dy dt is the derivative of y, which is going to be 3t squared plus 1. Dx dt is the derivative of x, which is going to be 4t cubed plus 0. And I'm trying to see what the slope is specifically when t is equal to -1. So I'm just going to plug in t equal to -1. And here's the notation for that. We draw a little vertical line, and then we write a little subscript with t equal to -1. So we plug in -1, and we get 3 times -1 squared plus 1 over 4 times -1 cubed, which is going to be 3 plus 1 divided by -4, which is -4 over -4, which is -1. So kind of unexcitingly, our slope is also -1, but okay. Now we need the point. Well, to find the x and y coordinates, we're just going to plug in the t value. So the x coordinate is going to be -1 to the fourth plus 1, which is 1 plus 1, which is 2. The y coordinate is going to be -1 cubed plus -1, which is -1 minus 1, which is -2. So my equation using my slope and my point is going to be y minus -2 equal to -1 times x minus 2. You could leave it like this, but we often like to simplify it so it's like a y equals mx plus b form. So that would be y plus 2 equals -x plus 2. And here the 2's happen to cancel. And our equation is y equal to -x. So that's the equation of the line tangent to this curve when t equals -1. Okay, we should go back to that. Yeah, we got decent amount of time here. So let's do one more example like this before we do that other thing. Actually. So let's look at this next example. There's so many, so kind of the problem with parametric curves is like, there's so many things to say about, like, you talk about first derivative, second derivative, area, and so on. So we'll do another first, second derivative thing, and then we'll talk about a little bit about area for a second. So let's look at this example where we have x equal to 4t cubed plus 3t and y equal to t squared plus 1. And let's just find the first and second derivative. So first derivative. Again, I would not recommend writing y prime in this context because y prime is unclear whether you mean dy dt or dy dx. So we really want to find dy dx, which is equal to dy dt divided by dx dt. So in this case, let's see, dy dt is 2t. Dx dt is going to be 12t squared plus 3. Which doesn't look like it simplifies very much, which is going to be unfortunate when we find the second derivative. Oh well. So second derivative. So we're going to have d squared y dx squared. And that's going to be equal to the derivative with respect to t of dy dx over the dx dt. So on top, we're going to have the derivative with respect to t of what we have right up there, 2t over 12t squared plus 3. We probably are going to have to use the quotient rule here. On the bottom, dx dt is going to be, again, so the nice thing about this process is the bottom here is the same as the bottom that you have from before. It's going to be, again, 12t squared plus 3. Let's make this look a little less terrible. I'm going to write this as 1 over 12t squared plus 3 times the derivative of 2t over 12t squared plus 3, sorry. Just to make it not have fractions and fractions. So now we're going to use the quotient rule. We still have the 1 over 12t squared plus 3 times quotient rule. It's going to be the bottom multiplied by the derivative of the top, which is 2, minus the top, which is 2t, times the derivative of the bottom, which is going to be 24t, all divided by the denominator squared. It's 12t squared plus 3 quantity squared. What's convenient here is that this and this happen to be the same, so we can combine those together and get 12t squared plus 3 quantity cubed as our denominator. So our second derivative is going to equal, well, the denominator at least is going to be 12t squared plus 3 quantity cubed. If we multiply out the numerator, we're going to get 24t squared plus 6 minus 48t squared, which ends up being 6 minus 24t squared over the same denominator. And then I would factor a little bit because we're probably going to want to do something with this. So I'm going to factor out a 6 from the top and say I have 6 times 1 minus 4t squared all over 12t squared plus 3 cubed. Okay, so now let's answer the question, where is this concave up and down? So, do I have enough room on this page? Maybe not. Sure, we can go up here. So where is this concave up versus concave down? So again, when you're asking the question about concavity, you're just asking about the sign of the second derivative. So we're asking, where is the second derivative positive and where is the second derivative negative? I would point out that the denominator of this second derivative is always positive. 12t squared is always greater than or equal to 0. 12t squared plus 3 is always greater than or equal to 3. So my denominator is always positive. So I really, really only need to look at where is the numerator going to be positive or negative. So let's see, where is 1 minus 4t squared going to equal 0? Well, solving for t, that's going to be 1 equal to 4t squared, 1/4 equal to t squared. The square root of 1/4 is 1/2, so plus or minus 1/2 is equal to t. So on my number line, those are the two numbers that actually matter. Positive 1/2 and negative 1/2. So if I look now at any number larger than 1/2, let's say 1, 1, sure, 1's fine. If you plug in 1 to my second derivative here, let's label this here, this is d squared y, dx squared. If you plug in 1, well, we already know the denominator is positive, because it's always positive. Plug into the numerator, 1 minus 4 is negative. So it's going to be negative over here, which means it's going to be concave down. Between negative 1/2 and positive 1/2, I would plug in the only reasonable choice feels like 0. If we plug in 0, we get 6 times 1 minus 0 is 1. The denominator is still positive, so the positive over positive is just going to be positive. So it's concave up there. And then when you pick a number smaller than negative 1/2, like negative 1, negative 1 squared is positive 1, and 1 minus 4 is negative. The bottom is still positive, so the whole thing's negative. So it looks like this is concave down when t is either from negative infinity to negative 1/2 or 1/2 to infinity, and it's concave up when t is between negative 1/2 and 1/2. But you can't really talk about the x and y values as easily when you're talking about the intervals of concavity for something like this. Kind of funky. All right, let's talk about another thing, which is, well, actually, we're going to go back and we're going to parameterize one more thing, or talk about the parameterization of one more thing. So let's talk about the cycloid. So very easy to describe. The cycloid is what happens if you take one point on a wheel, and as the wheel rolls forward, you trace out where that point goes. What people think about, like, is if you would like to drive over a fly or a marble and it got stuck in your wheel, the path of that would trace out as the wheel rotated around and the car was moving forward. So the way I usually draw it is I think about, okay, I've got some circle of radius r, and we think about the circle rotating forward. So we're going, that way, and it's rotating this way. I'm going to start with the point at the origin. So, my wheel was rotating forward, and I ran over a stone and picked it up in the tire. So now that stone is going to move in this sort of way. When the wheel has rotated a full 180 degrees, meaning whatever the radius is, will have traveled a distance of pi times the radius, because the circumference of the wheel is 2 pi times the radius. So if I think of, pi, there. So this distance is about, or is, pi times the radius. And when I've gone pi radians, I've exactly done half a revolution. So at that point right there, the stone that was on the bottom of the wheel is now at the top of the wheel. So I'm kind of tracing out this path, looks something like this. And then after another 180 degrees of revolution, or pi radians of revolution, we're going to end up back in the same orientation we were at the beginning, where the stone is on the bottom of the wheel. There's another pi radians, and over here, The stone's going to end up back on the bottom. Should be symmetric. So this path here, this red path, is the cycloid. And it should look a little more symmetrical than it appears to be as I've drawn it. But it takes a full 2 pi worth of an angle to do 1 full revolution. And in that 360 degrees of revolution, or 2 pi radians, you're exactly going to travel a distance of 2 pi times the radius, because that's how much wheel length there is in 1 full revolution. Parameterizing this is actually kind of terrible. I'm going to just give it to us instead of deriving it because it's a little bit awful. In Cartesian coordinates, you really don't want to know this. I would not recommend writing this down, actually. In fact, I'm hesitant to actually write it down, but I will. So the Cartesian coordinates are x equal to r times the inverse cosine of 1 minus y over r minus the square root of y times 2r minus y, where r is just whatever the radius is. That seems really awful. Much nicer if we parameterize it, the parametric equations, or coordinates, whatever word you want to use. X is going to be equal to r times t minus sine of t, and y is going to be equal to r times 1 minus cosine of t. And I'll be frank, the way I've always remembered this in my life is that it always looks exactly like the derivative of x is equal to y. Derivative of t is 1, the derivative of sine of t is cosine of t. So if you're trying to remember the parametric equations for the cycloid, you can think of it that way. It's not because of that, but it just happens to be. So notably, I'll point out, let's think about plotting a few points here. If time is equal to 0, then the x value is going to be 0 minus sine of 0, which is 0. And the y value is going to be r times 1 minus cosine of 0, which is r times 1 minus 1, which is also 0. Oops, I always forget to plug. You can have my plug out here. All right. Not my best work today. There we go. Okay. If we go to, say, an angle of pi, meaning we've gone through a half a revolution, now my x value is going to be r times pi minus sine of pi. Sine of pi is 0, so you get r times pi, which isn't surprising because look, the coordinate here, the x coordinate is r times pi. And the y coordinate, if I plug in pi here, cosine of pi is -1. 1 minus -1 is 2. So I get r times 2. And that's exactly that coordinate right there. My x coordinate is pi times r. And my y coordinate is exactly the diameter of the circle, which is twice the radius. And just to be a little complete here, if we go a full revolution, we're going to expect that the x coordinate is 2 pi r and the y coordinate is 0. And it is. If I plug in 2 pi minus sine of 2 pi, sine of 2 pi is still 0. So I get r times 2 pi. And if I plug in 2 pi here, cosine of 2 pi is 1, and 1 minus 1 is 0. So yeah, it seems reasonable that this is the actual parameterization of this curve we are describing. It's a pretty common example that instructors like to refer to and use, so I definitely think it's worth showing you. But let's talk about, well, actually, I will point out, we're not going to do it yet, but if you look at that, it certainly looks like it's concave down over the whole entire thing. And this is one period of it. It just repeats after that, right? It looks the same again and again and again. So we would expect this graph to actually always be concave down. But let's talk about a more interesting aspect of it. Let's talk about the area under it. So how do you find the area under a curve defined parametrically? Well, the way we always do. Just kidding. I mean, I'm not really kidding, but it's going to start off that way. So area under a curve defined parametrically. it almost feels like we're cheating when we do a lot of these. It kind of feels just like we're like doing magic tricks. We're just going to move this over here and it's going to work. So here's how it works. We're going to say, well, the area is equal to the integral of y times dx. But really, what we can think of is, well, dx is really dx dt times dt. And y is just a function of t, right? Y is equal to whatever y is as a function of t. So this is really equal to y of t times x prime of t dt. Some books do a thing where they say like y is equal to f of t and x is equal to g of t, and then they say this is f of x times g prime of t dt. It seems unnecessary to me. So in this case, using still the same parameterization, that x is equal to r times times t minus sine of t, and y is equal to r times 1 minus cosine of t, then we're going to end up getting the integral of y, which is r times 1 minus cosine of t, times x prime, which happens to be the same, right? The derivative of x is r times 1 minus cosine of t. Let's label things here just to be clear. That's my y of t. It's my x prime of t. Sorry, I got a little ahead of myself here. I should have said I want the area. So specifically here, this is the area under one period of the cycloid. Meaning we're going to let t go from 0 to 2 pi because that's how much angle we need to get one full revolution of the wheel. And then we multiply it out and integrate it. So we're going to end up getting the integral from 0 to 2 pi. R times r, let's pull that out in front and say we've got r squared. And you have 1 minus cosine times 1 minus cosine, which is going to be 1 minus 2 cosine of t plus cosine squared t dt. And this is the unfortunate situation where you have to do the thing using a trig identity for cosine squared. It does get a little bit less nice. This is going to be equaling r squared times the interval from 0 to 2 pi of 1 minus 2 cosine of t. And cosine squared t, we're going to replace that with the trig identity, which is going to be 1 plus cosine of 2 times t divided by 2. It's how we always deal with integrating an even power of sine or cosine. Is cosine squared t is equal to 1 plus cosine 2t over 2. Sine squared t, just as a reminder, sine squared t is equal to 1 minus cosine of 2 times t divided by 2. And then to make it a little bit easier before we finish it, I'm going to factor out a 1/2 because I don't want to deal with this fraction. So let's make this r squared over 2. So what I'm really doing when I factor out a 1/2 is I'm just multiplying the insides by 2. I'm dividing by 1/2, which is the same as multiplying by 2. So I have a now 2 minus 4 cosine of t plus 1 plus cosine of 2t. And now I think we're ready to integrate. Yes, I know the 2 plus 1 is 3. So when I integrate this, I'm going to get r squared over 2 out in front times the antiderivative of 2 plus 1 is 3t. It's an anti-differentiating 3. Right, that's going to be this part and this part. I just didn't want to write this line again. I figured we could just combine them together and anti-differentiate them. The antiderivative of negative 4 cosine of t is going to be negative 4 sine of t. And the antiderivative of cosine of 2t is going to be plus sine of 2t divided by 2. And this problem always feels kind of terrible, but then when you get to the end, everything becomes really easy. So if you plug in 2 pi, here's what you get. You get r squared over 2 times 3 times 2 pi. And now check out what happens with the rest. You're going to get 4 times sine of 2 pi, which is 0. And you get sine of 4 pi over 2, which is also 0. Because sine of any multiple of pi is always going to be 0. Minus, if you plug in 0, you're going to get 0 minus sine of 0, which is 0, plus sine of 0, which is 0. So in the end, we end up getting 3 pi times r squared. Or in other words, 3 times the area of the circle that was rotating. So I think it's kind of wildly interesting, personally, that when you do this, when you let this circle of radius r rotate 1 full revolution, the area under this 1 point that gets drawn out ends up being exactly 3 circles worth of area. It's kind of cool as far as math things go. Okay. Yeah, we have enough time. So one more example, or one more thing about this. So far, just to recap, here's what we've said so far. We've said that for parametric curves, we have the following things. We have that the derivative dy dx is equal to dy dt over dx dt. We have the second derivative, d squared y over dx squared is equal to the derivative with respect to t of dy dx over dx dt. And then you literally take what you have here and plug it in there, and then take the derivative of it with respect to t. Thirdly, we just talked about the area under a parametric curve, where we have y equal to some function of t and x equal to some function of t, is going to be given by the integral from whatever your appropriate limits of integration are of y of t times the derivative of x of t dt. And fourthly, the thing we're about to do is the length. So the arc length of a parametric curve. I know we've talked about arc length before, where we said it was, in fact, we did this before we actually did it parametrically. So I'll remind you and refer back to something we did before, because we're running a long time here. I'll just tell you, the arc length is going to be given by the integral from t equals a to t equals b. Instead of being the square root of 1 plus dy dx squared, it's going to be the square root of d, which way do I write this? Yeah, dx dt squared plus dy dt squared dt, which we briefly talked about a while ago. So it is something that's not totally out of the realm of reasonableness. But that's kind of that's what I always refer to as the third version of the arc length formula. So it can either be the square root of 1 plus the derivative of y squared, or the square root of 1 plus the derivative of x squared, or if it's parametric, it can be the square root of the derivative of x squared plus the derivative of x squared. All of them are valid. It just depends on which one makes the most sense to use. So for this problem, we can find the arc length of one cycloid. So that's going to be the integral from 0 to 2 pi of the square root of our dx dt squared. Sorry, yeah, that's fine. Dx dt squared, which is, let's actually write it down. Let me not get too far out of myself here. X is r times t minus sine t. Y is r times 1 minus cosine t. So our dx dt is going to be r times 1 minus cosine t. We're going to square that. And our dy dt is going to be r times 0 plus sine of t. So r times sine of t squared. And then we're going to simplify this. I'll point out that's my dx dt. Here's my dy dt. So check out how this simplifies. It's going to be the integral from 0 to 2 pi. We're going to the square root of r squared times 1 minus 2 cosine t plus cosine squared t plus r squared times sine squared of t. We can factor out the r squared. This becomes the square root of r squared is r times the integral from 0 to 2 pi of the square root of 1 minus 2 cosine t plus cosine squared t plus sine squared t. And here's where we notice the trig identity. Cosine squared t plus sine squared t is equal to 1. So we're going to rewrite this as something that doesn't look very kind. The integral from 0 to 2 pi of the square root of 1 plus 1 is 2. We have 2 minus 2 cosine of t. Yeah, how do I want to do this? I never do it that way. What is the so okay, no, I'm not going to do it. So here's what I have noticed over the years. This kind of looks like a trig identity I just talked about. It is true that sine squared of t is equal to 1 minus cosine of 2t over 2. So I could multiply both sides by 4 and say 4 sine squared of t is equal to 2 times 1 minus cosine of 2t. And then I could replace the t with t divided by 2 and say that 4 sine squared of t divided by 2 is equal to 2 times 1 minus cosine of 2 times t divided by 2. Oh, look. So I will fully admit, this is not something I would have known to do right away when I first saw this. This definitely comes from the experience of seeing this trig identity over and over and over again. When you see a 1 minus cosine or something times 1 minus cosine or 1 plus cosine in a square root, this is often the route we go. So we can say that 2 minus 2 cosine, which is what we have inside the square root, is equal to 4 sine squared of t over 2. So we can completely rewrite this as r times the integral from 0 to 2 pi of the square root of 4 times sine squared of t over 2. We have to be a little bit careful here. It is true that the square root of 4 is 2. The square root of sine squared is the absolute value of sine. I'm out of time. So I'll just say, so this is going to be the integral from 0 to 2 pi of 2 times sine of t over 2. We don't have to worry about the absolute value because sine of t over 2 is always positive from 0 to 2 pi, because t over 2 goes from 0 to pi, and sine is positive in quadrant 1 and 2. So then we can integrate this and get r times 2 times negative cosine of t over 2 divided by 1/2 from 0 to 2 pi. I wish I had more room on this piece of paper. So simplifying this a tiny, tiny bit, we end up getting negative 4r cosine of t over 2 from 0 to 2 pi. We plug in, we get negative 4r cosine of 2 pi over 2 minus negative 4r times cosine of 0. And that ends up being negative 4r times negative 1 plus 4r times cosine of 0 is positive 1. So you end up getting 8r. Which again, I just think is kind of interesting that this cycloid thing, which I've lost my picture of now. Sorry, it's gone forever. I just had it. Yeah. So that Again, this curve here, that's just this circle rolling out, one for evolution, that length is exactly 8 times the radius of the circle. I mean, I guess it's not totally unreasonable that the length would be related to the radius of the circle, but it just seems interesting that it's exactly 8 times worth the radius of the circle. Anyway, that is all I have. It is 4:33. I should stop talking. I should have stopped talking 3 minutes ago. So those are the 4 equations I would encourage you to try to retain as far as parametric equations go. We might talk about one more, which is the surface area. But if you know how to find arc length, you know how to find surface area. The surface area is just 2 pi times the radius times the arc length formula. But we'll talk about that next. Thanks for hanging in there with me today. Sorry I was not quite on the top of my game. Of course, of course. Yeah, sometimes you read a thing that you've known a long time and you're like, why is that true again? Let me look at that again. And then you're like, oh, I can't justify it in my head why that really